Simulating complex scientific models on the computer or processing large volumes of data, such as editing video material, takes considerable computing power and time. Researchers from FAU and the University of Rochester in New York have demonstrated how the speed of fundamental computing operations could be increased in the future to up to 1,000,000 times faster using laser pulses. The computing speed of today's computer and smartphone processors is given by field effect transistors. In the competition to produce faster devices, the size of these transistors is constantly decreased to fit as many together as possible onto chips. Modern computers already operate at the breathtaking speed of several gigahertz, which translates to several billion computing operations per second. The latest transistors measure only 0.000005 millimeters in size, the equivalent of just a few atoms. There are limits to how far chip manufacturers can go, and at a certain point it won't be possible to make transistors any smaller. Physicists are working hard to control electronics with light waves. The oscillation of a light wave takes approximately 1 femtosecond, which is 1/1,000,000th of 1/1000,000th of a second. Controlling electrical signals with light could make the computers of the future over 1,000,000 times faster, which is the aim of the petahertz signal processing or light wave electronics. Electronics are designed to transfer and process signals and data in the form of logical information using binary logic 1 and 0. These signals may also take the form of current pulses. In their experiments, the researchers illuminate a structure of graphene and gold electrodes with ultra-short laser pulses. The laser pulses induce electron waves in the graphene, which move toward the gold electrodes, where they are measured as current pulses and can be processed as information. Depending on where the laser pulse hits the surface, the electron waves spread differently. This creates two types of current pulses, which are known as real and virtual charges. The laser physicists at FAU have been able to demonstrate with their experiments for the first time that this method can be used to operate a logic gate, a key element in computer processors. The logic gate regulates how the incoming binary information 0 and 1 is processed. The gate requires two input signals. Here, electron waves from real and virtual charges excited by two synchronized laser pulses. Depending on the direction and strength of the two waves, the resulting current pulse is either aggregated or erased. Once again, the electrical signal that the physicists measure can be interpreted as binary logic 0 or 1. Franco, a researcher from Rochester, says, "This is an excellent example of how basic research can lead to development of new technology. Through fundamental theory and its connection with the experiments, we have uncovered the role of real and virtual charges, which has opened the way to the creation of ultra-fast logic gates." Meanwhile, at the University of Innsbruck, Austria, a team of experimental physicists has now implemented a universal set of computational operations on fault-tolerant quantum bits, for the first time demonstrating how an algorithm can be programmed on a quantum computer so that errors do not spoil the result. In modern computers, errors during the processing and storage of information have become a rarity due to high-quality fabrication. However, for critical applications where even single errors can have serious effects, error correction mechanisms based on the redundancy of the processed data are still used. Quantum computers are inherently much more susceptible to disturbances and will thus probably always require error correction mechanisms, because otherwise errors will propagate uncontrolled in the system and information will be lost. Because the fundamental laws of quantum mechanics forbid copying quantum information, redundancy can be achieved by distributing logical quantum information into an entangled state of several physical systems, for example, multiple individual atoms. The team of researchers implemented this universal gate set on an ion-trapped quantum computer featuring 16 trapped atoms. The quantum information was stored in two logical quantum bits, each distributed over 7 atoms. Now, for the first time, it has been possible to implement two computational gates on these fault-tolerant quantum bits, which are necessary for a universal set of gates, a computational operation on two quantum bits and a logical T-gate, which is particularly difficult to implement on fault-tolerant quantum bits. The physicists have demonstrated all the building blocks for fault-tolerant computing on a quantum computer. The task now is to implement these methods on larger and hence more useful quantum computers. The methods demonstrated in Innsbruck on an ion-trap quantum computer can also be used on other architectures for quantum computers. Speaking of computing, researchers from the University of Cambridge have used a widespread species of blue-green algae to power a microprocessor continuously for a year and counting, using nothing but ambient light and water. The system has the potential as a reliable and renewable way to power small devices. The system, comparable in size to an AA battery, contains a type of non-toxic algae called Prosthesis that naturally harvests energy from the sun through photosynthesis. The tiny electrical current this generates then interacts with an aluminium electrode and is used to power a microprocessor. The system is made of common, inexpensive and largely recyclable materials. This means it could easily be replicated hundreds of thousands of times to power large numbers of small devices as part of the Internet of Things. The researchers say it is likely to be most useful in off-grid situations or remote locations where small amounts of power can be very beneficial. In the experiment, the device was used to power an ARM Cortex M0+, which is a microprocessor used widely in the Internet of Things devices. It operated in a domestic environment and semi-outdoor conditions under natural light and associated temperature fluctuations. And after 6 months of continuous power production, the results were submitted for publication. The algae does not need feeding because it creates its own food as it photosynthesizes. And despite the fact that photosynthesis requires light, the device can even continue producing power during periods of darkness. The researchers think this is because the algae processes some of its food when there is no light, and this continues to generate an electrical current. The first author, Bombelli, says, "We were impressed by how consistently the system worked over a long period of time. We thought it might stop after a few weeks, but it just kept going." This is not the only thing that algae is useful for. Researchers at the University of Göttingen studied a specific group of lipids called long-chain diols that are found in sea sediments all over the world and that can be preserved for millions of years. The researchers discovered that these lipids are produced by until now an unknown group of marine stigmatophyte algae, which evolved before the currently known species originated. This finding changes our understanding of the composition and evolution of these algae, as previously they were considered to consist of a relatively small group of mainly soil and freshwater species. In addition, the researchers showed that a ratio of these distinctive lipids, known as the long-chain diol index, can be used to reconstruct summer sea surface temperatures from the past. The first author, Dr. Rampan, say a wide variety of techniques can be used to deduce ancient climates across Earth's history. What is exciting about our discovery is that we have demonstrated that the ratio of these unique lipids reveals temperatures in the warmest months. This explains why readings obtained by this method sometimes differ from other temperature reconstructions that give average temperatures across the year. Combining different methods now provides complementary information to help us better understand the Earth's climate going back millions of years. In other news, researchers at the Institute of Solid State Physics at the TU Graz have succeeded in developing the 3-in-1 hybrid material Smart Skin for the next generation of artificial electronic skin using a novel process. The skin is the largest sensory organ and at the same time the protective coat of the human being. It feels several sensory inputs at the same time and reports information about humidity, temperature and pressure to the brain. For almost 6 years, the team worked on the development of Smart Skin as part of the project Smart Core. With 2000 individual sensors per square millimeter, the hybrid material is even more sensitive than a human fingertip. Each of these sensors consists of a unique combination of materials, a smart polymer in the form of a hydrogel inside and a shell of piezoelectric zinc oxide. The individual sensor layers are very thin and at the same time equipped with sensor elements covering the entire surface. Several fields of application are now opening up for the skin-like hybrid material. In healthcare, for example, the sensor material could independently detect microorganisms and report them accordingly. Also conceivable are prostheses that give the wearer information about temperature or humidity, or robots that can perceive their environment more sensitively. On the path to application, Smart Skin scores with a decisive advantage. The sensory nanorods, the smart core of the material, are produced using a vapor-based manufacturing process. This process is already well established in production plants for integrated circuits. For example, the production of the Smart Skin can thus be easily scaled and implemented in existing production lines. Lastly, engineers at MIT and the Technical University of Munich have designed a new kind of glucose fuel cell that converts glucose directly into electricity. The device is smaller than other proposed glucose fuel cells, measuring just 400 nanometers thick, or about 1 by 100 the diameter of a human hair. The sugary power source generates about 43 microwatts per square centimeter of electricity, achieving the highest power density of any glucose fuel cell to date under ambient conditions. The new device is also resilient and able to withstand temperatures up to 600 degrees Celsius. If incorporated into a medical implant, the fuel cell could remain stable through the high-temperature sterilization process required for all implantable devices. The heart of the new device is made from ceramic, a material that retains its electrochemical properties even at high temperatures and miniature scales. The team sandwiched the electrolyte with an anode and cathode made of platinum, a stable material that readily reacts with glucose. They fabricated 150 individual glucose fuel cells on a chip, each about 400 nanometers thin and about 300 micrometers wide, about the width of 30 human hairs. They patterned the cells onto silicon wafers, showing that the devices can be paired with a common semiconductor material. They then measured the current produced by each cell as they flowed a solution of glucose over each wafer in a custom fabricated test station. They found many cells produced a peak voltage of about 80 milliwatts. Given the size of each cell, this output is the highest power density of any existing glucose fuel cell design. The researchers envisioned the new design could be made into ultra-thin films or coatings and wrapped around implants to passively power electronics using the body's abundant glucose supply. The developer Simon says glucose is everywhere in the body, and the idea is to harvest this readily available energy and use it to power implantable devices. In our work, we show a new glucose fuel cell electrochemistry. That's it for this video. Do let us know your valuable thoughts on these technologies in the comments.